Christophe. You can find me on Twitter or GitHub, on the left top there. I'm from Belgium. I like beer. You have some good ones. I'm the board member of Ruby Belgium, and I organize there several stuff like the conference RRCamp. So if you are a pirate, you should come. I'm also the founder of Pull Review, which is an automated code review service for Ruby and Rails. And I'm also a freelancer developing simulator of disease for pharmaceutical companies. And I would like to talk a little bit about that, but in a fun way. And, you know, zombies. So, at first, we heard a few cases of a rare disease in some villages. They were reported by the local newspaper, and it was a kind of rabbi that pushes people biting other. It sounded like, you know, something very sensational, feeding conspirationists. But 2 weeks after, the disease was obviously serious, mortal, and very contagious. The army has already taken action, you know, set up curfews, quarantines. Some zones were even condemned. The World Health Organization sent some experts to help the CDC and the army. You know, the epidemic must be contained. In those situations, your life is at stake. You need to survive, but you are just a software developer. What you can do, you can write some code. Could you survive with that? Maybe not. In fact, maybe you could. So yes, I think you can prepare yourself against zombie epidemic with code. So there are several techniques to simulate disease, and the one I would like to present you is Agentbased model, because it's really adapted when you want to get insight at the individual level. And because here we want to understand how it happens between zombies and sane people, this is the correct one to use. So we think maybe it's very specific to study of propagation of disease, but it's not. So you can also, of course, study propagation of disease like flu, especially outbreaks, considering flight routes. You can also study traffic jams and try to find the best configuration of lights and signalization to reduce that traffic jam. It's also used to simulate electrical consumption and its impact on the electrical grid. So you can understand when an outage can occur and what you can do to prevent it. It's also used to understand how the backbone of internet is robust or not, and take some action to make it more robust. And it helps also to predict behavior in group of persons, for instance, on the stock market, or during a crisis, or even to understand the network of trust in a social network. So as you probably noticed, it's suited to dynamics resulting of interaction between same components, such as persons, in a given environment. So if we want to simulate how zombies can spread, we need to define what an agent is, what's an environment, where they live, where they evolve, and the rules of interaction between them to understand how they evolve and behave according to the environment and the other agents. So let's start with the environment. Because zombies disease is very physical, it's important to have an environment capturing that. So we'll start with something very simple, like a map, a bidimensional map. And the other things we need to define is proximity. So we will have on that map a notion of neighborhood. So when two agents, as you see on the bottom, two agents are on the cross, we'll consider them neighbors, and then there is a possibility of contact between them. So we have an environment, now we can define our agents and their capabilities. So an agent has a state which is defined by its age, its position, and its health state. During the simulation, the agent can do different things. It can perceive its surrounding to know if there's someone in the neighborhood. It can accomplish different actions. So in our case, it can stay, walk, or fight. So walking will move the agent in the given direction. Staying will do nothing. And fighting is more a state where the agent is capable to fight back, or in the case of the zombie, to bite. An agent can, of course, age, become older. And finally, all of that will make the simulation. The simulation consists in calculating the next state of every agent based on the environment, the other state of other agents, and its previous state. So to make it simple, we have what we call a synchronous update, which is mean that we will calculate all the next states of all agents based on the previous one. And when it's done, we will update the current state with the new state. So we have environment, we have agent. So now we need to define what's the health state. This is the picture of rabies disease. So, for instance, we can have what we call a susceptible health state. It's when an agent is not protected against a disease, and it could be infected. So for each state, what we also do, as you see on the bottom, is to define the kind of action it can do. So in the case of susceptible state, it can walk, it can stay, or it can fight. And thanks to that, the panel of possible action depends on the health state of the agent. So for instance, for the zombie, he can only fight, bite, or walk. A zombie always walk. We can also define the condition of transition from a state to another. So here you have an example where we go from susceptible to infected state. And you see in the lambda that the condition is always true. It means that the transition will always occur. And of course, when you consider the different possible transition from a state to another, we can trigger it and obtain the new state that we can apply to the agent. So all of these will help us to define what we call a state transition machine. And this is basically what defines and handles all the possible transition and between the different states. So in our case, as you see on the diagram, we have 4 different cases, states. Susceptible on the left, that I have already explained. Infected, when it's a susceptible agent that has been bitten by a zombie, and he has the virus, but is not yet a zombie. It just incubates the disease. The Z is the zombie state, and the X on the bottom is when the agent is really dead. That could be applied to the zombie or healthy agents. And then you have the different possible transition between the different states. So for instance, from infected to zombie state, it occurs after a certain period, which is the incubation period. And it will occur after 2 days, for instance. From Z to X, it's when the susceptible or infected agent fight back, and they win, and they are able to kill the zombie, and so on. We have also to define a default initial state to set the initial state of all agents. So with all of that, we need to simulate the things, and we define a loop. So basically, the whole simulation consists in that loop that we will go through. So let's say we'll simulate 100 days. We create all the agents and put them on the map. And for each step, we do the following. For each agent, they can act and then age. So at that moment, we will calculate the new state of the agent. And then at the bottom, we'll commit that new state for every agent. And then we remove the dead from the map. That's it. So here you have two examples. So in green, you have the susceptible agent, the healthy one. In yellow, the infected one. In red, the zombies. And in black, sometimes it pops up. They are the dead. So on the left side, the future is not bright. And on the right side, they're pretty good at fighting back, and you have a happy end at the end. So, a couple of remarks. When your simulator is implemented, you still need to validate it and calibrate it. Just a few words about that. So validation is kind of integration test. You want to check that your simulator behaves as expected in certain situations, like if you have only susceptible agents, they will be safe forever. But also you can consider some theoretical models or real data, and you want to compare your result with your simulator with those data and check that you obtain what is expected. For a few values, for a few parameters, you don't know the exact value you need to use, and the process to find those values is called the calibration. So what you will do is to try different values and in order to obtain a given output, and when you have that output, you know that the values are correct. And when you have that, you can say that your model is able to predict the propagation of the disease. So I will show you quickly the simulator to end the talk. Okay. So on the left, you have the simulation. So as explained, the colors are the same. What I did is I disable all the possible transition that was defined. And now I will uncomment some of them. So for instance, well, sorry. So here you have a transition where when you have a susceptible, you will check the neighborhood, and if there's a zombie into the neighbor, and he is in mode fight, and that in all the cases, we'll consider that he will infect that susceptible agent. Normally, we should go to infected states. So I will save, and now you will see some yellow colors appearing. They are all the infected agents. This transition define, as you saw, everything came red. It's because this transition define that after 2 days, if you were into the infected state, you should become a zombie. And you see that everybody now is a zombie. So now I will rerun the thing. Let's consider that the zombies are really bad at that the healthy agents are really good at fighting back the zombies, and that we have a version of zombies that are very bad at biting healthy agents. So you see there, normally the zombie will disappear, and that's it, we win. So I will come back to the presentation. Whoops. Sorry, yeah. I can show more complex behaviors, but it's to give you an idea that even with a simple implementation, you can already do stuff. And actually, it's really inspired by one of the work I did, and it could be as simple as that. And you will be able to understand, according to some behaviors, the kind of what could be the outcome of the epidemic. And so you can try some strategy as vaccination or quarantine to find a way to protect yourself against the disease. And that's it. The code is available on GitHub and Twitter. If you want to talk with me, if you have some question, I can answer them now. And also, if you have some question about peer review, we can do that after the talk, during the break. Thanks.